Hello everyone, welcome to the lecture series on computer vision, and for today's discussion we have here the concept that is shape from shading. So what actually the shading is? Shading is nothing but it is a variable levels of darkness. Like if you observe the three images which I have placed here. So in the first image I am having a cat, and in the second image you can see a circular shape. I don't know what exactly it is. It may be a circular plate with some thickness, or it may be a sphere, but I don't know. So if I would like to know what actually the shape that is present in the image is, if I want to know, means definitely I have to have the variable levels of darkness. The same thing I have depicted here. Okay, so the same image, whatever the image that I am having here, the same image I also have taken here also, but here it is having variable levels of darkness. That means here the darker area is more, because this part is covered with more darker area, and when compared to this part we can see that there is no such dark region. So that means, can I say this image which is having some object inside it is possessing some variable levels of darkness. So if it is possessing some variable levels of darkness, means can I consider now that this image object, the object that is present in the image, is exhibiting various intensity levels? That means the intensity levels possessed by this object are not uniform. Okay, so the intensity levels exhibited by this object is not uniform, means it is giving me some perception that it is a 3D object, right? Because the same perception I cannot get from this image, but when compared to this image I can have here a 3D kind of perception. Okay, so here also you can see, in the first image I have a cat. So this cat is having some kind of variations in its intensity levels. The cat object is having variable levels of intensity levels. So that means I can able to perceive that it is a 3D object, or it is a 3D image. Okay, now that means a 3D object is present in this 2D image. Okay, now according to the shading, that means this image and this image is exhibiting the variable levels of darkness, and because of the presence of this shading concept, I may get a compelling perception of my 3D shape. So from here and from here I am able to get some 3D object perception. And so as I have said you that it is exhibiting variable level of darkness, means definitely the intensity varies. So that means because of the intensity variation, here I can able to trace out what actually the shape of the object that is present in the image. So when you compare with this figure, I cannot able to trace out what is the shape, because I am in the perception that it may be a circular disc with some thickness. But here when compared to here, I will definitely perceive it as some 3D object. So based on the intensity levels, I can justify that it is a kind of a 3D object. It is some kind of a shape, that is a 3D shape. Okay, and because of this intensity, it is giving me a strong feeling of the shape or the object structure. Now, like our brain is having an excellent like brain simplifies here. What actually it does, it can easily interpret the shape, because by seeing this scene or this scene, what our brain do, it can easily interpret the shape or the structure by this image only. That means what is the thing that is present in this image is, it is some kind of a shading. So by seeing the shading that is present in the image, so brain simplifies the task of interpreting the shape from shading. Okay, so but computer vision, do the computer vision also have the capability, or it is having any ability to trace out the shape or a structure from the given shaded image? Let us see, will it do or not? Okay, so that means here from a single 2D image with various intensity levels, here I can able to reconstruct a 3D shape information, a 3D object information. If I want to, I will be able to reconstruct a 3D shape information. That means if I want to get. So that is the concept of shape from the shading. Now, the shape from shading is an ill-posed inverse problem. Why it is an ill-posed inverse problem? Because here many shapes can give rise to the same image. As we have already discussed an example for this concept. So here I am having a source of illumination, and this is my first case, and the below one is my second case. The source of light, the source of light is striking these two surfaces. One is blue in color and one is white in color. So I am going to get here some kind of plots. One is a reflectance and one is an illuminance plot. Okay. So the reflectance for these two surfaces is uniformly I am getting, but here I am getting illuminance in this way. Okay. But when I capture the same thing by using a camera, I am getting a 2D images. So I have got my 2D image in this manner here, and the same source of light, if it is striking these two surfaces, I will be getting my reflectancy as well as my illuminance plot in this manner. And after capturing through a camera this scene, I will be getting my 2D images in this structure. So now the 2D, because by using these 2D images, can I exactly can I exactly get the information about the 3D scene what I have captured? Definitely here it fails. That is why, as I have said you, that many shapes can give rise to the same image. So this kind of a shape or this kind of a shape is giving you the same 2D image information. So the same concept I am taking here one more example for the explanation purpose. So a person is doing some hand gesture here. So the shadow of this person hands gestures are what they are on the wall. So the shadow is present on the wall. Okay, that means by seeing this shadow, I can able to visualize that is some kind of an object which is nothing but a small puppy is present here. By seeing this shadow that is present in the image, I perceive that a puppy is present in this image. But truly speaking, it is not a puppy. Why? Because it is the result of some hand gesture done by a person. Like for example, this entire image is there. If I have partitioned into two segments, the left one and the right one, and the left one is completely the shadow thing. Okay, so this by giving input this 2D image, that is shadow, what I feel or I perceive that it is the shadow of a puppy. But truly speaking, it is not the shadow of a puppy, but it is a hand gesture's shadow. Okay, so that means, can I say now many shapes are giving the same 2D information or can give rise to the same image, 2D images. Okay, so here we can't reconstruct the shape from one shadow. So what happens here? Now we have to assume that we should aware now of light source, lightning conditions, along with what the surface reflectance, that means whether it is a Lambertian surface or non-Lambertian surface, and also we need to consider about the albedo. The albedo should be uniform. Whenever we are tracing out or we are constructing a 3D, whenever we are interpreting a 3D information from the 2D image, given 2D image, okay, which is having a shading concept. Now, so that is why so we need to consider. So by using like how to interpret a 3D information from the image that is having a shadows or variable level of intensities or darkness. Now then how to do it? So for this purpose we do have here a solution. Like we need to represent a particular surface. Okay, so how to represent a particular surface here? So let me take a spherical surface here. So this because why I am considering this as a spherical surface means it is having a variable levels of darkness or variable intensity levels are present on this circular area. That is why it is giving me a perception that it is a sphere. So this sphere is having a smooth surface. If it is having a smooth surface means definitely it is going to have a tangent plane at every point, right? So let me construct a tangent plane at every point on the sphere. Okay, so for time being I am having here a tangent plane I have taken here, where you can see here. And by using by using this normal component at every point on the sphere, so how this normal component I am getting, as I have considered each and every point on a tangent plane, definitely I will be getting a normal component. So I can like interpret that 3D information once I find the normal components everywhere on the surface of the sphere. So what actually happens, that means if I have a grayscale image and also if I know what are the lighting conditions and what will be the albedo that is present, I can able to reconstruct the scene geometry as I have if I have the information of the surface normals. Okay, so that means if I have an information on normal component, I can able to interpret what actually the 3D scene information is. Okay, now let's discuss a small concept here, that is radiosity. So what is this radiosity? Okay, now you can you can see here in the right side there is a spotlight that is radiating its energy, and this energy is falling down towards this area. So in the area A1 and in the area A2, A1 is having more intensity because it is very nearer to the spotlight, and A2 is having a bit less intensity because it is a bit far away from the spotlight, from the source of light here. So what actually the radiosity is? Radiosity is nothing but it is a reflectance emitted by an object, right? So how this object, because you see, if you see this image is emitting some radiations, some light radiations are being emitted by this image, because of which I can able to get irradiancy in my image. That means the pixels present in the image of the image plane in the camera is having variable levels of darkness because of this emittance of the light, that is nothing but reflectancy of the light. So that means this scene is exhibiting the radiosity. So the radiosity here is nothing but it is a sum of your excitancy plus power reflected by the other surfaces. So what is this excitancy? So the excitancy of a surface is defined like this. It is the internally generated power radiated, because this power is generated here and it is being radiated. It is radiated here, you can see here, per unit area on the radiating surface, because this is an internally generated power. Because of this internally generated power, I am getting here the radiations. The radiations are being emitted here in this manner. The same thing you can see here. So this is a room where I have on the ceiling a lamp, ceiling lamp it is. So because of this lamp, it is having an internally generated power. Which power? Light power. So it is generating the light power. So the light rays are striking the surfaces that are present in the room, whatever the objects or whatever the floor surface. So after striking out, definitely the object will reflect the light. Yes or no? Right. So that means, can I say an object or a source can have a radiosity or it also can have an excitancy. So here the lamp is having excitancy because it is an internally generated power is being radiated in the form of light rays. So this is an internally generated power. And coming to the this one, radiosity is nothing but because it reflects. Okay, so this entire thing is now reflecting. So radiosity is nothing but excitancy plus power reflected by the other surface. So I am getting out here in the image or in the scene some kind of a radiosity is being exposed. So this is the concept of the radiosity. Now what is this seen radiance then? So the seen radiance, it actually depends on the amount of light. So if I am having a source of light like this here, the amount of light falling on the surface plus the fraction of light that is being reflected. So if it is the fraction of light being reflected means definitely an albedo will be coming into the concept here, because if it is reflected and this light ray is being captured by your camera or your eye, so definitely albedo concept will be coming into the picture. And also the seen radiance also depends on the geometry of light reflection. That means from where your light is being reflected. So that means we need to consider here the shape of a source and also the viewpoint from where I am viewing this point. Okay, so viewpoint as well as the shape of the surface. Okay, that means it is a seen radiancy. Okay, so the seen radiancy depends on all these three parameters. Okay, now if a light ray is being captured by your camera or an eye and you are going to get an image in your image plane, definitely an image will be having its some irradiancy. That means some kind of light rays are being collected by per unit area, per unit surface area, means it is what it is comes under the category concept of irradiancy. That means it is receiving something. So who is receiving here? Some camera is my object that is receiving something, that is capturing something. So irradiant, so if it is capturing something means it is taking or it is receiving the irradiancy. That means someone have to radiate. So this object is radiating as it is showing or transmitting its radiancy and it is receiving the irradiance, right? Now what is its irradiancy? That is I. Okay, so here I is nothing but here irradiance. So irradiance is can be expressed as rho n dot s. It is a dot product. Then what is the rho here? Rho is nothing but the albedo of your surface, and n is your normal component and s is the source of light vector. So here the source of light is present in a 3D environment, so definitely it is going to have some vector. Okay, because if I have if I suppose I have assumed this source of light as a point source, point means definitely in my 3D coordinate system it will be having its own coordinates. So I can also represent this source of light with some vector notation. Similarly, if the normal component is also going to have some kind of a vector notation or the representation. Okay, now by using, so that means if I consider the surface, if it is a Lambertian surface for suppose, now can I say the radiance leaving from the surface is independent of angle, right? Because not in a particular direction it reflects, it may reflect in any other direction. It is as per the surface wish. Okay, so that means radiance leaving from surface is independent of angle, as the surface appears equally bright. Because in the yesterday class we have taken an example of a diffused surface, Lambertian surfaces. We have taken or we have seen the cotton cloth, white papers, all are exhibiting the uniform intensities, right? So the surface appears equally bright from all the views. As the light here reflects without absorbing, because no specularity will be considered. So for the Lambertian surface, did you ever find there will be a concept of specular reflection? Definitely no. So that is why for the Lambertian surface, we don't have any concept of the specularity. That means the brightness of the surface as seen from the camera will be linear, and it will be correlated to the amount of light that is falling on your surface. So this is the concept of your irradiancy, how your irradiancy is related with your albedo as well as the source vector and the normal component of the point where the light is striking out. Okay. So what actually our objective is, we need to reconstruct the shape from the 2D images or from the scene or shape. That means the scene is having some kind of shading. So shape from shading is our objective now. Okay, so before it, let me like introduce you a terminology that is nothing but if suppose I am having yes gradient space. So what is this gradient space? So gradient is nothing but it is first difference or first differential form. Okay, so gradient space, let me assume I am having here x, y, z. It is a 3D coordinate system. So here it is my positive z direction. Here if I go means I will be having a negative z direction, and this side a positive x-axis. This will be my negative x-axis, positive y-axis, and downside negative y-axis. Consider a point here that is present at V. Okay. So if this point is present in this 3D space, definitely this point going to exhibit its location. So what if I would like to trace out where at what is the location of this point means, definitely I need to use the coordinate system, 3D coordinate system. So this point V is having the location at alpha, beta, gamma. At alpha, beta, gamma is the location of this point. Okay. Now if this point is projected on the image plane, definitely I will miss with the 3D coordinate. That means I have here only two coordinates. Third coordinate will be missing if I capture anything, if I capture any 3D object. So 3D object means it is a three-dimensional coordinate system, it will be present, and if that object is captured means in the image I can trace out that object only under the 2D coordinate system. So 3D coordinate is, third coordinate is missing here, you can see as P, Q. So that means here the point V is moved alpha units from the z-axis towards x-axis. This point V is moved beta units from z-axis towards the y-axis, and this point V is moved from the origin gamma units. So actually I need to figure it out like this, the point V, because if I take this one as my origin, so this point V is moved gamma units away from the z-axis, alpha units away from the x-axis, and beta units away from the y-axis. So that means from the origin, actually it is not from the y-axis. So that means the point V is moved from the origin alpha, beta, gamma units from the origin. That means alpha represents this is alpha is parallel to x-axis, beta is parallel to y-axis, and the gamma is parallel to your z-axis. Now This point is projected in the image plane. Definitely I will be having only two coordinates. Like, can I say this point V is in negative z plane? Because if this is my positive z plane means it is a negative z plane. Okay, so there will be gamma will be a negative component obviously. Okay, now so in the image surface, if instead of p comma q, if I have assumed like this, if this is let it be an x comma y, okay, so because it is the x and y coordinates, right? So let the imaged surface be z equal to f of xy, which is in xy plane. So this is xy plane. Okay, so then its surface normal can be obtained as a cross product of, because if it is in xy plane means definitely it will, this v is perpendicular to x coordinate and y coordinate, right? So definitely that means I can now tell you that it will be a normal component. So normal component, how I am going to obtain here is just I am doing the cross product of the two surface vectors. So what are the two surface vectors here? It is 1 0 dou f by dou x, 0 1 dou f by dou y. So if I do the cross product for these two vectors, I am going to get my surface normal. So now can I say that pq minus 1 is the surface normal now by seeing this one? So if it is projected in the image means it is p comma q. So point V is projected on this image plane. That means this V I can assume it is a normal component for the surface xy. Right. So p comma q comma minus 1 is the surface normal. So the same thing I am explaining by taking one more example. It is my z axis, it is my x axis, and it is my y axis. So there is some rectangular plate which is initially placed on the ground. So what is the ground here? xy. Your xy surface is the ground. So this is my x comma y. One of the corner of your rectangular plate is at x comma y. Now what I am doing here, the main thing here is surface orientation. So that means I be orienting this surface now. Let me orient, that means let me have some tilt for this surface. So the surface orientation can be parameterized by the partial derivatives of your z. So this partial derivative concept is nothing but your this one gradient space comes into picture. Okay, so before it, like my surface plate is there which was initially grounded. Now what I am doing, so I am not disturbing my z plane. Okay, so I am not, sorry, I am meant to say that I am not disturbing my y, because this y, this side, this line is there now, this line. So I am not at all disturbing, but what I am doing here, from this, previously my plate is placed on the ground here. Now I am slowly raising my plate. So up to now my plate got raised. Okay, up to now my plate got raised means, can I say that previously my length of the plate is this one, right? Now can I say the same length will be there now, because it is decreases, it generally decreases, because now the new length will be dx. Okay, so now like in the similar manner, the plate which was now currently is raised, okay, like this, now it is raised now in the y direction, because it is my x plane and it is my y plane, sorry, it is my x axis, it is my y axis. Now from here I am raising my plane. So like the initially it was like this, in this manner, like this. Now what, I'm not disturbing this one, I'm not at all disturbing this thing, but I am raising the other end of the plate. Previously I raised this end of the plate. Now what I am doing, I am doing now raising this end of the plate. So this edge of the plate is being raised. Okay, so for how much I have raised is nothing but it is dy. So here for how much quantity I have raised in the x direction, it is dx. So that means, can I say now like the plate like the plate got raised, means it underwent some tilt along the x direction as well as the along the y direction. So how much amount of tilt? Okay, now P equal to dou z by dou x and Q equal to dou z by dou y. This is what I will be getting. So that means here the P and Q are nothing but the gradient values. So what are the gradient values, how they are defined here? This P is nothing but differentiating your z with respect to x, because this edge of your plate got moved up or taken up, and in the next time your y, so the other end of the other side of your plate got tilted up. That means it is differentiated with respect to y axis. So it may not have the previous previous y value, it may not have. Here also it may not have the previous x length, it may not have the previous y length. So definitely the y and x length varies. So according to the concept, P and Q are nothing but here the gradient values. What they are? They are the gradient values. Here Z is not at all changing. So Z is with respect to x, it got differentiated. Z here with respect to y, it got differentiated. So the surface normal is given by, one is due to one component, because this is the raising due to x and this is raising due to y. Okay, the other end of the plate. Okay, so p01 are the vectors and ry is the 0q1 are the vectors, because these rx and ry are the vectors that are present in your 3D environment. That is why I have considered a 3D vector here, 3-dimensional, because 3D coordinate system. Now if I would like to get a normal component, means normal component is to whom it should be a normal component? To the surface, where the surface initially it was like resting in the xy plane. So towards the normal perpendicular to your like tangent plane, your normal component should happen. So that means the normal component, can I say now, it is the cross product of your Rx and Ry. So once you do the cross product for this one, you are going to get here P comma Q comma minus 1. Okay, so the vector n, so this normal component can also be normalized in this manner, that is n by magnitude of n, P comma Q comma minus 1 by root of P square plus Q square plus 1. This is how I will be getting the normalized vector. So you can take this one, or you can follow this one as an example about the surface orientation. So whenever, definitely in our environment of 3D coordinate system, and if we are capturing any object, we never be having a parallel alignment. Definitely the camera or the object what we capture will definitely undergo some tilt or some orientation. So orientation, if it is undergoing, means definitely a concept of gradient space, that is P comma Q gradient vectors will be coming into the picture. Now with the help of the surface orientation, we have found the surface vectors which carries the information about the gradient values, that are P and Q. So Once we know the value of P and Q, which are nothing but these are the gradient values. Now the dependency of the surface radiance is proportional to the local surface orientation, which is expressed in terms of gradient space. So what is this gradient space? So gradient space is nothing but it is a space which are mastered by your gradient. What are the gradient values? Here we have obtained the P and Q are the gradient values. So now the surface radiancy is depending on the local surface orientation as well as the reflectance map. So what is this reflectance map actually is? The reflectance map R of P comma Q, it captures the surface orientation and as well as the brightness. Okay, at a particular point in the image, we measure the image irradiancy at some point. The image irradiancy is, let us assume it is E of x comma y. It is image irradiancy. That is why I have used the notation E. So this irradiance is proportional to the radiance at a corresponding point on the surface imaged. So for example, I am having this figure. This is my image plane. So at this point, the irradiancy is proportional to this point. So this point is being captured by your camera and in the image plane, this point is observed here. So this irradiancy is proportional to the point, this point radiance, right? Okay, so this irradiancy is proportional to the radiance at the corresponding point on the surface imaged. So that was the surface being imaged. If the surface gradient at that point is P comma Q, then the radiance there is R of P comma Q. So for suppose so let me assume this as my point. So at this point my radiance will be what now? It is R of P comma Q. But in the image plane, what are the coordinates for that point? It is P comma Q. So if the surface gradient at that point is P comma Q, then the radiance there is R of P comma Q. So normalizing, for suppose I just wanted to normalize, means can I write that the irradiancy, because P of Q is nothing but what? It is capturing something, it is receiving something, means it is receiving what? It is receiving the radiancy that is emitted by that point. So E of x comma y is equal to R of P comma Q. This is what I got finally. Now, so this Lambertian surface, that means for the Lambertian surface, which are diffused surfaces which exhibit a uniform brightness, the reflectance map R of P comma Q is given by, what is this R of P comma Q? Radiance reflectance map is given by N dot, yes, it is the dot product, that is normal component to that point as well as source vector. So if PS QS minus 1 is my source vector, so and if P comma Q comma minus 1 is my normal component, and here the radiancy is given by what? It is simply, it is a dot product of your normal component and a source vector, that is 1 plus PSP plus QSQ by under root of P square plus Q square plus 1 into under root of PS square plus QS square plus 1. So this is how I have got my reflectancy map, which is depending on the surface orientation as well as the brightness. Okay, so the reflectance map of an image R of P comma Q can be, so if this is my reflectancy, right, at this point this is my image, so this is a 3D object, this 3D object is having various intensity levels. So at this point I am having some intensity level, so this is reflecting, this point is reflecting. So this reflectancy map, that is R of P comma Q, this can be visualized in my P comma Q gradient space. That means here these are nothing but P and Q are nothing but what? as we are having in our 2D coordinate system x-axis, y-axis, in the 3D coordinate system x, y, z, 3D Cartesian coordinate systems. Similarly, in the gradient space, so we call this space as now a gradient space because these are mastered by the gradient values p and q. Okay. So these p and q, how they are obtained? They are obtained by the surface orientation, by the tilt in x direction, or it may be in the y direction. So this is p and q are nothing but the gradient values. So this this is p axis and this is my q axis. So this is nothing but your gradient space. So this reflectancy map, that is R of p comma q here, can be expressed or can be visualized in my pq space, pq dimension space as a nested iso counters, because you can see here a counter that is circular in shape. So this counter is one more counter, this is one more counter, one more counter, like this, like this, like this, like this. So this 1.0 is nothing but this one. This point is nothing but it is a 1.0. That means it is purely white. So next is 0.9, next is 0.8, next is 0.7, in this manner. So once you observe here, the R of p comma q can be visualized in the gradient space, means this R of p comma q now going to have some value. So what is the intensity value, or what is the brightness, or what is its radiance you are expecting here? It is R of p comma q is nothing but it is 0.7. This reflectancy map is completely dependent on your surface orientation as well as your brightness. So like ISO bright, this all the things are nothing but here ISO brightness counters, because for different brightness values we are able to get a different ISO counters. So these ISO counters of the reflectance map of a Lambert surface are a set of conic sections in a gradient space, because this is in the shape of a cone, this is a kind of a conic shape. So we majorly get in a structure of conic shape. That means here the brightness is a function of the surface orientation, that is p and q values. Now if my ps qs are here, so if my p equal to ps and q equal to ps, that means can I say R of p comma q will be having a value that is 1.0, because here it is the value is R of p comma q, the value here is it is 1.0. Okay, so that means it is having the highest brightness, right? Okay, now like next slide, you can see here these are three different images of a sphere with different shadings. One is a lighter shading, one is purely darker shading, and one is a ambiguous shading. That means some part is light and some part is dark here. So that means this first image is resembling this image, right, a bit. So now here in the first sphere, majority is in white section or it is in lighter space. So the ISO counters are found towards this direction. Okay, that means towards the positive first quadrant of your PQ gradient space, because more number of ISO counter lines will be found here itself. Coming to the darker one, the darker sphere, which I can assume that more number of darker pixels are present. Okay, so that means if darker pixels are present in this sphere, means because of the shading effect, my ISO counter will be in the third quadrant of the PQ space, like this. Okay, so for different intensity values, or for at every point I may not have the same intensity, so at every pixel I may have a different R of p comma q value. Why? Because here at this point, that is R of p comma q, I have got here as R of p comma q equal to 0.7. That means along this direction, for any value of p or q, your reflectance map for this point is r of p comma q will be 0.7 for any value of p or for any value of q here. So because this ISO counter is having your value as 0.7, where you can take any point on this curve, it gives you the reflectance map as 0.7. So for coming to the center image, it is a bit lighter image. So lighter image means the gradient space will be appeared in this manner. Okay, that means here the brightness, the light is focused on the center, and slowly if you are moving towards the edge of the sphere, it became darker. That means it is what the effect what we get from this kind of a shading image is, this is my reflectance map, gradient space. This is my gradient space. That means the brightness of an image is this one, and the corresponding reflectance map will be this one. So these reflectance maps are traced by the ISO counters. So a counter in PQ space of constant intensity is given by C equal to N dot S, because we have seen this one here itself only, R of P comma Q, that means the radiance at that point that is being imaged, R of P comma Q equal to normal component dot the source vector, that is 1 plus PSP plus QSQ by root of P square plus Q square plus 1 into root of PS square plus QS square plus 1. So it is a counter, ISO counter, because it is a reflectance map. Now for each intensity value, okay, so for each intensity value and for each source direction, there is a counter on which a surface orientation could lie. Now if you see here, because like my light direction is assume it is in this direction, so the light will be present or it will strike the top where you can have a good brightness, but at the back side of the sphere which is not in contact with the incoming light rays, so the back side of the sphere, this part, you can feel a darker region, as a darker region. So that means here the brightness values are changes because of the source of light or because of the source of illumination of the image. And so that means for each intensity value and for each source direction, there will be a counter on which a surface orientation could lie. So let us take this an example. So for this darker pixels, so okay, for this point I am having this counter. If you move towards here at this point, I may have a 1 as a counter. If you move towards this point, I may have some kind of 0.1 or 0.2 or then less than 0.0 also I may have a counter. So depending on the brightness as well as the source orientation, and sorry, I meant to say it is a surface, because of the surface orientation, and also I need to consider the from where the illumination I am facing, I am going to get my different ISO counters. These ISO counters are the result of the brightness values that are being imaged. Okay. So finally, the image irradiance. So what is this? The image irradiance is related to the scene radiance as what? So if I assume this one as x comma y coordinate, that means I have mentioned you that this point is nothing but it is this point that is being imaged here. So I of x comma y is nothing but, so from here I am getting the reflection, that means reflectance map at this point is what? It is r of n of x comma y, because if I have to assume through the normal component, I will be taking x comma y as a notation. So if I want to express this one in the gradient space, by considering the surface orientation of this surface, I will be using the R of P comma Q. That means the surface normal can be represented this surface normal n of x comma y using the gradient space representation. So that means as I have also discussed with you, the normal component is nothing but your gradient space only. Gradient values, the vector which is carrying the gradient values is nothing but the normal component for that surface point. So the image irradiance can be represented as I of x comma y equal to R of P comma Q. In this manner we got. So now it is very much clear that each point in an image is characterized by, because if you consider this image or this is characterized by what? It is nothing but some kind of an intensity. This intensity is happened because of the lighting condition. Okay, this intensity because of some different lighting condition, So as well as the surface orientation. Now some bit of orientation I can find out in these three images. A small bit of orientation. Okay. Now to recover these two parameters, that means like what are the parameters here? Intensity as well as the surface orientation. So why do I require these two parameters? Because what is my objective? The objective is nothing but the shape from shading. So to recover these two parameters from a single image and to achieve the actual object, that is shape from shading, we use here a concept called photometric stereo. So what is the concept of this photometric stereo? So before going to this concept, if I want to interpret or if I want to recover my 3D image characters from the given 2D image, if I want to produce a 3D object properties or model from the given 2D image, means I need to get the surface normal of that image. That means the normal components first I need to trace out. Okay, so you remember this point. So what is the concept of the photometric stereo here? So it needs several images. So the same images under the same viewpoint. Okay, so now like so, these three images are in the same viewpoint actually. Okay, now assume these three images are in the same viewpoint with different lighting condition. So the light is for this image, the light is somewhere here, and for this image the light is above some top, and for this image the light is at the right side, it got placed. So to estimate the 3D shape of the object in the images and the albedo of the surface. So what the albedo of the surface we need to know. So to estimate the 3D shape, main target of ours is to estimate the 3D shape of the object from the images. Okay, so we go with the photometric stereo. Before it, in this image, in this scene, this is gradient space, that is reflectance map. First image, second image and third image with same viewpoint but different lighting conditions, right? So at this point I got my ISO counter in the gradient space in this manner, like this, the brown color lines. For this image, the green spot, the same point with different color. So I got my ISO counter in this manner, in green in color. Okay, and for this one, for blue, I got here my ISO counter in this manner. So the intersection of these three ISO counters will be giving me a 3D object. So I can able to reconstruct my 3D shape or 3D model I can able to reconstruct. So that means I can from the thing, that means I can able to trace out here the surface normals by which I can able to get here the 3D reconstruction. You can see here. Now this is the face, the same views but different lighting condition. Here the lighting is taken, each striking from the right side. The light is placed right side. Here the light is placed left side of the image, and here the light is placed front side, and here some ambient light. Assume it is an ambient light. So once I take all these ISO counters, I am going to get the 3D model in this manner. So now that means different lighting conditions is the concept that is present in the photometric stereo. So in the photometric stereo, I am having a light source 1, light source 2 and light source 3. Let me assume this is my x comma y coordinate, and my camera is placed here. So this surface is in xy space or xy plane. Now shall I represent my surface x comma y in this manner in the 3D coordinate system? X comma y is the surface, f of x comma y is nothing but it is the intensity value, that is brightness. And this kind of a representation is nothing but Monge patch representation. So in this representation, f of x comma y is the depth map of the surface at the point x comma y, because here you can see x comma y. So this x comma y point is in some valley region. So if you observe this point, it is in some upper region, and if you observe this point, it is in some lower region. If you observe this point, it is in upper region. That means as it is not a uniform surface, because we are having many pits and ups here, many ups and downs are there in this surface. So that means because of this, I may have a chance to get different depth information. So in this representation, f of x comma y is nothing but different depth. So this nothing but different brightness I can face, different or variation in the brightness values can be observed if I capture that surface by using my camera. So that means if variations in the brightness observed means definitely the image contains shading. So shading is present means I have a chance to get the 3D information from the given 2D image. So the camera is linear here, you can see the camera. So this is the one. The camera is kept, it is linear, we are assuming. So in the photometric stereo, the input is some object, okay, with different lighting condition, but this object is kept in the same pose. So by which if this light is on and these two lights are off means I will be getting one image. If this light is on, these two are off means I will be getting different image, and if this is on, these two are off means I will be getting one more different image. So by using the concept of photometric stereo, the output where I can able to reproduce or construct the 3D shape of the object from the series of images, and also I can able to find out by considering the factors like albedo and lighting conditions also have to be taken into the consideration. So let's come to the concept here. So in this representation, f of x comma y is nothing but it is the depth map of the surface at a point x comma y. So the camera is linear, and so the value of pixel at x comma y is given by what? This is image irradiance. I of x comma y is nothing but k rho n s. So from where we have got this concept? From here. Yeah, so this is image irradiance is nothing but it is n dot s. So what is rho here? Rho is nothing but albedo, n is the normal component, s is the surface vector component. Okay, so I equal to rho n s. So why this x comma y? Because I am focusing on this coordinate on the surface. So this location on the surface. So I of x comma y equal to k into rho of x comma y n of x comma y dot s1. So dot s1 means it is the dot product. Now what is this k? It is nothing but it is a camera constant. K is nothing but a camera, simply a camera constant. Rho of x comma y is nothing but it is a surface albedo, it is a surface normal, and S1 is nothing but because we may have here plenty number of sources. Okay, so sources S, this is light source 1, so S1, light source 2, S2, light source 3, S3, like that. So I of x comma y, by using this light source I will be getting one image. Okay, by using different light sources I will be getting different images. Now let me assume that rho of x comma y into, that is its normal multiplication, n of x comma y, I assumed it as r of x comma y now. So, and as well as k s1, because it is some kind of a scalar quantity, it is multiplied with s1. Now considering I am having n number of light sources, for each of which Ci is known, because same Ci, right? Definitely it is not. This Ci is nothing but it is k into s1. So here the light sources are different. Okay, so but these light sources are still in our hand. We know what the properties of these light sources, so we know this parameter is in our hand definitely, and k is also the one which is in our hand. Definitely I will be knowing that C1 is also in my hand. So considering n sources for each of which Ci is known, we can form a matrix that is C equal to C1, C2, C3, C4 up to Cn. So n number of sources results in n number of C. Now for each image point, we can group image pixel values as a vector. So I1 of x comma y is resulted by what? I1 of x comma y is resulted by S1 source. I2 of x comma y is resulted by S2 source. These S1 source or S2 source are kept in different directions. So they are the source of light. So by which at the same point I am going to get different what the brightness values, that is irradiance values. I of x comma y equal to I1 of x comma y, I2 of x comma y up to In of x comma y. This is the transpose. So there would be one vector per image point x comma y, and each vector has all the image brightness. So because this vector is having all the image brightness observed at that particular point, because these all are the brightness values that are resulted from different light sources. So can I write now? It is a generalized equation as I equal to R into C. It is because I equal to K rho N S. Ks is C, rho N is R. That means can I write as I equal to RC? Yes, of or CR. So C I know, R I don't know. The relevant elements of the matrix. So this is nothing but I of x comma y. This is a shading matrix. Why it is a shading matrix means I1 of x comma y, this is the brightness value that is obtained from the source S1. This is obtained from the source S2. In of x comma y, this is the brightness value obtained by the nth source. Okay, if I consider three sources means I3 of x comma y, I have to write for that point. Okay, so I accumulated all the irradiance values into a matrix form. So because of this, because it exhibits kind of a shading, right? For different light, different shading I may get on the image. So I accumulated all these things and I have got in a matrix form I of x comma y like this representation. Now what I do? This one I just multiply with this equation. So I of x comma y is a generalized equation, CR of x comma y is a generalized equation. So this equation, this I is nothing but this one, okay, and this small I is nothing but it is also what, it is a vector form, this one. I1 of x comma y, I2 of x comma y. This is a transpose I have set u. So it will be in this manner. It will be in a vertical it is n cross 1 matrix or n cross 1. Yeah, it is a n cross 1 matrix. It is an n cross n matrix. Now I can do the multiplication. Finally I have got in this manner. Okay, so I of x comma y, CR of x comma y. Now what is this I of x comma y? The same thing I have produced here. Okay, so C is nothing but this. What is C here? C equal to a camera constant into the source of light. So camera constant is in my hands. Source of light is also the known factor for me. So what I am going to get here? So C into R. C is nothing but it is a n cross 1 matrix, again C1 transpose C2 C3 up to Cn into R of x comma y. Okay, but in the R of x comma y is nothing but what we have taken rho into n. Rho is the albedo, n is the normal component. My aim is to find the normal component, first one. So for many surfaces the albedo lies in between 0 and 1. Okay, so let me take the best case. So as 1, so n of x comma y is a unit normal for that point. So r equal to rho into n. So key substitute rho value as 1. Now can I write the rho of x comma y as r of x comma y now? Right? Okay, so because if it is a unit normal, okay, r of x comma y equal to rho of x comma y into n of x comma y. If this vector it is a unit normal for suppose. Now can I write rho of x comma y equal to r of x comma y? Definitely, yeah, I can able to write. Now the albedo can be determined from r of x comma y only. Okay, as follows. So I have found the albedo now, right? So also the surface normal can be recovered now as n of x comma y equal to r of x comma y by rho of x comma y. Instead of rho of x comma y, I am writing in this manner. Okay. Previously I have assumed it is a unit normal to trace out my rho of x comma y. Now I have found my rho of x comma y. Now what will be my surface normal? It is nothing but n of x comma y, that is r of x comma y by magnitude of r of x comma y. So to recover the depth map, that is f of x comma y, is to be computed, right? Now how it can be computed? That means it can be computed the depth map, like one will be valley, one will be high, one will be lower. So that means the structure of this shape can be found only until and unless I should know the normal vectors at each and every point. So the same thing here. So to recover the depth map f of x comma y, that means intensities for the understanding is to be computed from the estimated values of your unit normal, that is n of x comma y. So that means here, now let us consider three measured values r1, r2, r3. So what is this r? R is nothing but rho into n. So r is nothing but rho into n means albedo I know it may lie between 0 and 1. That means this r is proportional to n, right? So r is proportional to n. I got the normal component, I can able to trace out like this. So let us consider three measured values. Now r value can be measured as r1, r2, r3 because of three different light sources. So and also I have assumed it is a unit normal. I have assumed what? It is a unit normal. Okay, of unit normal at some point x comma y. Now r of x comma y is nothing but r1, r2, r3. Okay, so now according to the concept, I should find out the 3D object properties. So the 3D model I need to reconstruct. Means I should aware of the intensity values and also I need to aware of the gradient space values. Okay, and also the reflectance radiance of the at that point. So P comma Q I should know, right? So P comma Q, this P is with respect to X, okay, and this Q is obtained with respect to Y. That is the f of x comma y with respect to x. This is the surface orientation with respect to x direction, and Q is nothing but it is a surface orientation with respect to y direction. So P is traced out like this in this manner: r1 of x comma y by r3 of x comma y. This is r2 of x comma y by r3 of x comma y. I have got now the P comma Q values. As we got the values of P and Q here, we can able to find out the surface vectors, which are Rx and Ry. So Rx and Ry we have already defined. Let me show you that one. Yeah, Rx and Ry are defined in this manner: Rx equal to P comma 0 comma 1, Ry equal to 0 comma Q comma 1. So by using these two vectors, surface vectors, we can able to find out the surface normal, which is given by the cross product of Rx and Ry. So finally the normalized component or the normalized vector what I will be getting here out is P comma Q comma minus 1 by root of P square plus Q square plus 1. I can calculate the normal component at that particular point. So this is my test of integrability principle, that is dou p by dou y should be dou q by dou x, and the surface is reconstructed in this manner. So f of x comma y equal to 1 is under the integration of x, second is under the integration of y. So this is fx of x comma y ds plus integration of 0 to y fy of x comma y dt plus c, where c is a constant. So that means I have found out here the surface normals are like this. For the surface, recovered normal field will be like this, and from this one, once I have got the normal vectors, means I can able to trace out how my 3D shape of the object. So surface recovered after the integration. So this is the concept. In this way, that means we need to finally find out the normal component. How the normal component can be found at each and every point. This is the ultimate equation. So this is the ultimate equation. If we got the information of normal component at each x comma y by this mathematical equation, we can able to get f of x comma y. The surface is reconstructed, that is f of x comma y. That means the depth value can be reconstructed by using this formula. Okay, so let me stop for today, and in the next class we discuss some more concepts. Have a nice day.